Hi, welcome to the final lecture for Math310, Simon Fraser University, spring of 2020. Today we're going to talk about sections 5.5 and 5.6 of the Boyce and DiPrima textbook, series solutions near a regular singular point. We will not be handling series solutions near an irregular singular point. So we're only going to be able to solve these equations near regular singular points at the end of this course. We saw last lecture how to distinguish between a regular and an irregular singular point. Okay, so here is our second order linear ordinary differential equation. P of x y double prime plus q of x y prime plus r of x y equals 0, and we are claiming in this that we have a regular singular point at x equals x naught, for which in fact we are going to make that 0. And that is not really much of a restriction. So if for example the regular singular point was not at 0, we could make a substitution to ensure this. So making the fact that it's 0 here is I mean, it's a restriction, but it's not a serious one. So let me just note that you can make a substitution to ensure this. Okay, so let's recall what it means for the point x equals 0 to be a regular singular point. That means the limit as x goes to 0 of x times p of x over, let's try that again, x times q of x, this function here, x times q of x over p of x, and the limit as x goes to 0 of x squared times r of x divided by p of x is finite. Also, we are stating in effect that x times p of x is analytic at x equals 0, meaning that it has a convergent power series. So x times p of x has a convergent power series, and x squared times q of x also has a convergent power series. Okay, so now we're going to see why the Euler equation was so important, because if we're going to try to solve any linear ordinary differential equation near a singular point, we can rearrange it to look like an Euler equation for which we already know how to solve. So let us take a look at how that works. We have the differential equation, capital P of x y double prime plus capital Q of x y prime plus r of x y equals 0. I'm going to divide through by capital P of x, yielding this equation here. There it is. So I have little p of x is going to be q of x over p of x, and I have little q of x being r of x over p of x. This is similar notation we've used throughout the course. So I'll just rewrite that here then, plus p, that's little p of x, y prime, plus little q of x, y, and that's 0. Okay, I'm going to multiply through by x squared. Multiply through by x squared. And I'll get this equation here, x squared y double prime plus x times x p of x. So I've just separated the x squared on that second term into two x's. You'll see why in just a moment. And then I have x squared q of x, y equals to 0. So what I want to do is focus on these two terms right here, right now, x p of x and x squared, this should be q of x squared q of x. We have just said that they are a regular singular point, and that means that they are analytic at x equals 0, and they have these convergent power series here. So I am going to substitute this power series in here. See, this is x squared q of x, and here is x squared q of x. This is xp of x, so this is xp of x. I'm going to substitute in those power series, which I know converge because the x equals 0 is a regular singular point. Okay, let me do that. That will then be x squared y double prime plus x times, I'm going to write the power series for xp of x in its expanded form. It looks like this: p naught plus p1x plus p2x squared plus dot 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 times y prime. And then the power series for x squared q of x looks like this: q naught plus q1 plus dot 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 q1x, let me put another couple of terms in here, q2x squared plus dot 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 times y, and that's equal to 0. Okay, then I will take a look at this power series, these power series near 0. So now I'm taking a look at what is here, this power series, and this power series here. And we are expanding these power series around x equals 0, and the regular singular point is at x equals 0. And so I am interested in the area in the neighborhood of 0. And this here is approximately equal to p naught when x is very small. In fact, it is equal to p naught as the limit. If I take x to 0, then these terms will disappear, and I will see that this is the only surviving term. So when I am very close to x equals 0, that term p naught dominates that power series. The same thing happens here. This thing here is very, very close to being equal to q naught, and in fact it is q naught as the limit as x goes to 0. So we are considering our solution in a neighborhood of the regular singular point, which is at 0. Okay, so if we make this assumption, we take Pn equals to Qn equals to 0 for all n not equal to 0. If we do that, which is exactly what I've described doing above, then the ordinary differential equation simplifies, and it simplifies to this: x squared y double prime plus x p naught y prime plus q naught y equals 0. Take a look at that. That is the Euler equation, which we already know how to solve. This is why it's so important to understand how to solve the Euler equation, because we can rearrange ordinary differential equations, any linear ordinary differential equations, to look like the Euler equation near their singular points, near their regular singular points. Okay, so we're going to use this piece of information to solve these types of equations. Okay, a really important point. And perhaps take enough time going through this derivation here to understand why these things will, near their regular singular points, will always look like Euler equations, because that is the key piece of information that you need in order to solve a linear ODE near its regular singular point. Okay, so the usual model will then apply. We're going to assume a solution of a particular form, and substitute in and find out what the coefficients are. Okay, so let us do that in this case. So we're going to just for simplicity, let's just do this, x greater than 0 for simplicity. While we're doing this derivation. So we have our ordinary differential equation. It looks like this. And I'm simply factoring out the P naught. It looks like this. And similarly, I will factor out the Q naught. And I will have this Q1 over Q naught x plus Q2 over Q naught x squared plus, keeping going, multiplied by y, and that is equal to 0. We have a homogeneous differential equation. Okay, and so we are going to then seek, therefore, we will seek series solutions of the form y equals x to the r. That's what we did for the Euler equation, multiplied by a power series. That's going to, in its more compact notation, look like this: x to the r times a power series, and then I can move that x to the r in, and I get a series, an infinite series that looks like this. Okay, what is different here? I mean, we need to find out, to solve this thing, we'll need to find r. That will be one of our goals, find r, and then find all the a_n's. Okay, but what is different here than when we had the series solutions before? I now have a proposed series solution for these types of equations, but this, in particular, this is not necessarily an integer, not in Z. Okay. R is going to be the root of an equation. It's not necessarily an integer, so r plus n is not an integer. So it is not a power series. It is a infinite series, but those exponents on x are not necessarily integers. So we have a special name for this type of series. We don't call it a Taylor series or a power series. We call this the Frobenius series. Let me just write this here. Y of x equals to this infinite sum here, n equals 0 to infinity of a n x to the r plus n is called a Frobenius series. Okay, so I'm not going to prove this, but I will state it. Every equation of the form px y double prime plus qx y prime plus rxy equals 0. So every linear homogeneous differential equation with a regular singular point at x equals 0 has at least one solution that is a Frobenius series. Okay, so the key feature of differentiating the Frobenius series from the Taylor series is the fact that this thing here is not an integer. It is, of course, possible that when solving one of these things, the r's from our what we're going to call the indicial equation, but which we've previously been calling the characteristic equation, can be integers, and this thing may well, in fact, simplify down to a regular power series, but that is not guaranteed. So in general, the index on those, the exponent on those, on these these x's here are non-integers, and that's what makes this a Frobenius series. And we are guaranteed to have at least one solution like this near a regular singular point. So let me just write what I've been saying down to make it really clear. It is generally the Frobenius series' solution. It is generally not a power series. Because r is not necessarily an integer. Okay, so now we are going to proceed as we always have. We have assumed now a solution. We're assuming our solution is the Frobenius series. So let me write that here, a n x to the r plus n. We will take the derivatives. We need the first and second derivative. So the first derivative will look like this, n equals 0 to infinity, and we will have a n r plus n x to the n plus r minus 1, and then our second derivative will look like this. The sum n equals 0 to infinity a n r plus n minus 1 x to the n plus r minus 2. Okay. So this is going to be the solution to the differential equation, and then this is the first derivative, and then this one here is the second derivative of the solution. Okay, so let us try an example. Here we have a differential equation, 2x squared multiplied by 1 plus x times y double prime plus 3x times 1 plus x all cubed y prime minus 1 minus x squared y equals to 0. So we're first going to try to find the exponents in the two possible Frobenius series of this equation. Okay, so we know we want to assume a solution of the form. Sorry about that. Let's just we want to assume a solution of the form y equals the sum from n equals 0 to infinity of a n x to the n plus r. And so what I want to do is I'm trying here to find r. Okay, that will allow me to, so here's my idea, to find the exponents in the two, what I mean here is find r. Depending on the equation I get, the quadratic equation and r I get, they'll either be 1 or 2 values of r. Okay, in order to do this, I'm going to divide through. Step 1, I'm going to divide through by 2x squared times 1 plus x. And that will give me the equation written in this format, y double prime plus 3x 1 plus x cubed divided by 2x squared 1 plus x minus 1 minus x squared divided by 2x squared 1 plus x y equals 0. Then I will rewrite this in the following manner. Y double prime plus 3 halves, and I'm going to cancel one of these x's here, this one here with the square on there. And I will get 3 halves 1 plus 2x plus x squared y prime all divided by x. Okay, how has that happened? This is algebra. I have expanded the cubic, and then I have divided by 1 minus x. Or I guess we could say, in fact, it would be smarter to cancel this 1 minus x with this and then expand the quadratic. So that would also work, and that would be faster. Okay, similarly, I'm going to rewrite this one here as minus 1/2, and then I will have it I'm thinking of this numerator here as being 1 plus x, 1 minus x, factoring that numerator, and then canceling the 1 plus x with the 1 plus x. And I'm going to write this like this then, 1/2 1 minus x divided by x squared, and that y, and that's equal to 0. Okay, I'm looking at this, and before I proceed, I'm doing a quick check, and I'm observing that if I would take this first coefficient, or take the coefficient on y prime, that's y prime. If I was to take the coefficient on y prime, this thing right here, I would multiply it by x. I would have a function that has a power series, and you can see what the power series is. It's simply the numerator. Okay, if that doesn't happen, then something has gone wrong. Similarly, if I take this coefficient here on y, I multiply it by x squared, I see that I have a function that has a convergent power series here in the numerator. Similarly, this, I'll just circle that one too. So both of those circled numerators in the coefficients on y prime and y have convergent power series near 0. Okay, so that's an important feature. Okay. I look at what the leading coefficient, the A0 coefficient on the power series is, and I can see now that I've manipulated this thing that P0 is equal to 3/2 and Q0 is equal to -1/2. Okay, so I'm looking at the power series of both of those numerators, and I'm identifying what is the constant term. So that's thinking of this like this: x squared y double prime plus x times P0 plus P1 x plus ... y prime plus Q0 plus Q1 x ... y equals 0. Okay. Right, so I've identified the P0 and the Q0 to be 3/2 and -1/2. Okay, so then I rewrite my ODE, or maybe what I might be more accurate to say is I rewrite the corresponding Euler equation to this ordinary differential equation here at singular point, and then that looks like this. Okay, so that's the corresponding Euler equation. You can see what I've done here is I have replaced what was previously, oh, there seems to be no Q0 here. Sorry, that Q0 is 1/2. So I have now a Euler equation, and in order to solve my Euler equation, I substitute, just like we did on the lecture on solving the Euler equation, I substitute x to the r. Okay, that for the solution to this this corresponding Euler equation, and I get a what I'm going to call, we would have typically been calling the, well, we did call the characteristic equation when we had constant coefficients and we substituted e to the RT. Now we're substituting x to the r. We're going to call this the indicial equation. So we get here it is, r times r minus 1. That comes from the second derivative, and then we get 3/2 r, that's coming from the first derivative, and then the 1/2, that's coming from the function. Okay, so we get an equation that we can solve for r. Let me just expand that and combine terms. So this would be, say, r squared minus r plus 3/2 r minus 1/2 equals 0, and that is r squared plus 1/2 r minus 1/2 equals 0. And we go to factor this over q, and we're going to get r plus 1, r minus 1/2 equals to 0. And that tells me then that r has two, we have two solutions. R is minus 1 and r is 1/2. So I've used the associated Euler equation to figure out what that number r is for my Frobenius series for the differential equation that I'm trying to solve. Okay, so therefore the two possible Frobenius series solutions are y1 of x is going to be x to the 1/2. That's corresponding to the r is 1/2. So this is the r equals 1/2 possibility. And sum n equals 0 to infinity an x to the n. The other solution will have this form: x to the -1 sum from n equals 0 to infinity bn x to the n. So now I have two functions which I would then propose as the solutions to my differential equation that I started with. Okay, so in this case, all is I've gone through as requested and find the values of r. So I found two of them. This is the r is equal to -1 solution, and then this is the r equals to 1/2 solution. Let's take a slightly simpler differential equation and go through the entire process finding the full solutions to the differential equation. So I'm just going to draw your attention to the different question that I posed here. Here I said find the exponents in the two possible Frobenius series solutions to the equation, which I have now done. And this one I'm going to actually find the full series solution to this differential equation. Okay. Right. So I'm going to follow exactly the same procedure. I'm going to divide through by this function right here, divide through by 2x squared. Divide by 2x squared. That yields this, y double prime plus 3/2 y prime divided by x plus -1/2 minus 1/2 x squared divided by x squared y equals 0. So I can see, again, I want to really emphasize this, that the x equals 0 is a regular singular point, because this thing here and this thing here both have power series representations that are convergent at x equals 0. So x equals 0 is a regular singular point. Okay, next step, you need to figure out what those values of r are. Okay. What am I doing then? I need to identify what is Q naught and P naught, and then write the associated Euler equation. So let me just notice from above here, I can see that P naught is 3/2 and that Q naught is -1/2. That is the constant term in the power series of those two numerators. So that allows me to, so now I'm thinking of the I don't necessarily have to write this out every time, but just so that we're clear, that allows me to be thinking along these lines here. X squared y double prime plus 3/2 x y prime minus 1/2 x y equals 0. The corresponding, need that x there, 1/2 y equals 0. That's the corresponding Euler equation. And that's what we saw the similar, in fact, the differential equation wasn't the same, but we saw the same two values for P naught and Q naught in the previous example. Okay, so allow me to then recognize, just as it was from before, that we have this equation here, r minus 1/2 times r plus 1 is equal to 0. That's coming from this r minus 1 plus 3/2 r minus 1/2 equals to 0. Okay, that gives us that r is a half and r is minus 1 as before. They don't differ by an integer. Okay, so they don't differ by an integer. Therefore, I have two Frobenius series as possible solutions to this differential equation. The first one looks like this, x to the 1/2, and then my power series. And my second one looks like this. Okay, so we are now going to take these proposed solutions and substitute them into the differential equation. And our goal here will be to figure out what all the a_n's and b_n's are, because once we've established what all these values are for a_n and b_n, these guys here, that defines exactly which Frobenius series we have, and that tells us what function we are looking at for the solution to our differential equation. Okay, I'm going to step 4. So I'm going to actually use y equals x to the r. So right now I'm going a little bit backwards. I'm not going to specify. Well, I'm going to change this to a c so we don't get confused. C n x to the n. I'm not going to specify whether r, this r that I have right here, I'm not going to specify whether it's a half or minus 1. That's just because a bunch of the work I can do with it unspecified, and that I don't have to do it twice. And then I can later, when I've done some amount of the work, I'm going to then specify which one of the two I mean and complete the project. But I can do a bunch of it doing them at the same time effectively. Okay, and I'm changing this C so that we don't, it's when r is a half, it's going to be the a's, and when r is minus 1, it's going to be the b's. But we're going to call it c so we can distinguish between the two of them. And let me get this Frobenius series correct. Oh yeah, I've got it correct there. Okay, so now what I'm going to do is move this into the inside here, this x to the r. I write the Frobenius series in this manner here. Looks like this. Y equals the sum n equals 0 to infinity Cn x to the n plus r. I take the first and second derivative. We've done this already. And then our second derivative like this. That is n plus r minus 2, the second derivative. Okay. Bearing in mind that I do know what r already is. I'm going to substitute into the original differential equation. So what do I mean by original? I mean not into the Euler equation or anything. I'm substituting in to the differential equation I am trying to solve. Substitute solutions into differential equation. This differential equation right here. Okay, that's the one I'm trying to solve. I'm going to substitute these Frobenius series solutions into that differential equation. And I get this thing here, 2 times the sum n equals 0 to infinity. So this is y double prime plus 3 times the sum to infinity n plus r Cn x to the n plus r minus the sum n equals 0 to infinity Cn x to the n plus r plus 2 minus the sum n equals 0 to infinity cn x to the n plus r, and that's all going to be equal to 0. So assure yourself that you can substitute y prime, and y double prime into that original differential equation and get this expression here. Then what's the next step? The next step is to shift the indices to make the exponents the same. Okay, so I will do that, and we'll get this here. This can be quite time consuming, as you can see. Okay, because of this n equals 2 here, I'm going to treat the, this shouldn't be n minus 2 here, this should be n plus r. They all have to be the same. So I shifted the indices to make the exponents the same. And because I've got that n equals 2 there, I'm going to treat the n equals 0 and n equals 1 case separately. So n equals 0 yields this for me. Yields this thing here, 2r minus 1 plus 3r minus 1 times c naught, which I'm going to simplify a little bit, 2 times r squared plus 1/2 r minus a half c naught equals to 0. That's the n equals 1 solution to this equation here. The n equals 0 solution. Now the n equals 1 solution gets you this here, 2r plus 1 times r plus 3r plus 1 minus 1 times c1 equals 2r squared plus 5r plus 2 c1 equals to 0. And I'm looking at these things here, and well, actually, I should. Why don't I? It is true, I'm looking at that, but let me look at it here in this simplified version. That is not 0. Okay, this thing here is non-zero for both r equals 1/2 and for r equals minus 1. And that yields me the information that c1 is equal to 0 for both r. Okay, I can't do that with this one. Okay, but I did get some information now. I know that for both of my series solutions up here that I'm proposing, I know that A1 and B1 are 0 because I know that C1 is 0 for both R. So I've figured out one coefficient in my infinite power series. Okay, I see here that my notes are here going to finding a series solution for the Bessel equation of order 0, which I am going to do, but I need a more space to figure out to finish the problem that I'm on, problem 6 that I'm on. So I am simply going to go down near the bottom and give myself a little bit more space here. Hang on, I think at this point it might be easier just to get another page. Let me do that. So I'm continuing the solution on another piece of paper here, add page. Okay, I've got some blank space. I'm going to now look at finding the rest of the coefficients on the example I'm working on. So I made this slightly confusing. I am still on this, I'm still looking at this differential equation here, 3xy prime minus x squared plus 1y equals 0. I have managed so far to figure out that r is equal to 1/2, or r is equal to -1, and I've managed to figure out that a1 is 0 and b1 is 0. I also have a recurrence relation of well, I have a relationship where I know something about C0 at this point. Let me just write out what that is. I know something about C0. Where am I at? I know this. 2r squared plus 1/2 r minus, well, actually I don't really know much about C0 because C0 is equal to 0, because this thing will be equal to 0 when r is 1/2, and let's see, when r is equal to -1, that's 1 minus 1/2 minus 1/2. Yes, it's also, so that thing is equal to 0 for both values of r. So I have no information yet on that, no info. Okay. All right, now let's take a look at the coefficients. Look at the coefficients. Look at the coefficients of x n plus r. Okay, how do we do that? Well, we know that for a polynomial to be equal, and we have a 0 polynomial on the right-hand side, that means that the coefficients on all the powers of x have to be 0 on the left-hand side. That means that 2 times n plus r, so this is all of the powers of x, the values of n starting from 2. We handled 0 and 1, and now this is all of the other ones, 2, 3, 4, 5, etc. So here we have okay. So then I have an expression that relates for me what is Cn in terms of Cn minus 2. So I'm going to solve for Cn, and I will find that Cn is equal to Cn minus 2 divided by 2 times n plus r squared plus n plus r minus 1. And this is true for n greater than or equal to 2, because that's this expression here is for n greater than or equal to 2. I handled the 0 and 1 case separately. Okay, so far I've done all this work and I have not said which value of r I am talking about. Now I'm going to separate into the two cases. So I managed to do quite a bit of work without having to separate into the two cases. So 7, separate into two cases. That's going to be, that is Cn is going to be, are going to be the ANs when r is equal to 1/2, and under the conditions, C0 is A0, and C1 is equal to 0, and that is A1. Okay, and then Cn will be Bn when r is equal to -1, and I have that C0 will be B0, and C1 will, which is 0, will be B1. Okay, so let's take now a look here. When r is equal to 1/2, that was good. I'm now taking this expression here for Cn. I am now fixing r to be 1/2. That's going to be allowing me to calculate the ANs. That's going to give me this recurrence relationship here. AN is AN minus 2, and substituting in r is equal to 1/2 into that, I get 2n squared plus 3n. Okay, that is this denominator here, evaluated when r is 1/2. Okay, I have that. I have this situation here. A1 is 0. A1 is 0. So that implies that AN is equal to 0 when n is odd. That's half of them done. And then when n is even, so it's equal to 2, 4, 6, etc., like that, we can use the recurrence relation to find these coefficients, and we get A2 is A0 over 14, A4 is A2 over 44, and that is A0 over 616. And I can then calculate so I can calculate now as many of these things as I want. A6, I go through A4 using the recurrence relationship, and then I substitute what I know is true for A4, and I get A0 over 55,440. Well, I can keep going, and that allows me now to write out the solution, the first of the two solutions for my differential equation. That is going to be y1 of x is going to be A0 x to the 1/2, and then 1 plus x squared over 14 plus x to the 4 over 616 plus x to the 6 over 55,440 plus ... There it is there. Then I can go and do exactly the same procedure on the r equals -1 case. So I have, all right, so I'm just going to draw a little line there. So I'm now looking at the other solution to my differential equation, the second solution, and I have that b1 is equal to 0. And so that, again, bn equals 0 when n is odd. Okay, and then plugging in r equals -1 into this equation here. Let me just point to it. I'm now looking at this equation again. And now I'm considering the case when r is equal to -1, plugging in r equals -1, and then now that is allowing me to talk about my second solution, and that is going to then be bn -2, and here's that denominator evaluated when r is equal to -1. Okay. Just like I did above, now I can calculate what is B2. B2 will be B0 over 2. B4 is B2 over 20, which is B0 over 40. And then I can figure out B6, and I can figure out as many of these as I wish. B4 over 54, and then that is B0 over 2,160. So then that allows me to write out my second solution. y2 of x is going to be b0 x to the -1, 1 plus x squared over 2 plus x to the 4 over 40 plus x to the 6 over 2160 plus ... And I am done. I mean, I have two solutions to my second order differential equation. Those initial constants that I don't know, A0 and B0, those will be determined by the initial conditions. So I have here, there's one solution, and there is my second solution. Hi, we're back with example 7 of the section on solving ODEs near a regular singular point. And this is a very important equation. This is the Bessel equation of order 0. This may be one of the most important functions in special functions in mathematics, and it's say, for example, particularly important in wave propagation. Let me just tell you why it's the Bessel equation of order 0. That is, the reason for that is the general form of the Bessel equation looks like this: x squared y double prime plus xy prime plus x squared minus alpha squared y equals 0. And you can see that what we're looking at over here, the equation we're going to solve, is with this alpha here equal to 0. So we're looking at the Bessel equation of order 0. So the first thing we're going to do is write it in standard form. I'm going to write it in standard form. Write in standard form. And that will ensure us that we're near a regular singular point, and also we'll be able to see what the P naught and Q naught are, the first two constant terms in the power series of the coefficient functions. So I'll write this in standard form looking like this: y double prime plus 1 over x y prime plus x squared y over y squared equals to 0. I'm particularly interested in understanding what the power series of this is and what the power series is here of these two functions. Okay, so I need to have here, so that have that convergent power series representation. I have this here and this here. Okay. All right, so now I can see that x equals 0 is a regular singular point. Once I've written my equation like this, x equals 0 is a regular singular point. It's the first thing I can see. The next thing I can see once I've written it like this is that P naught is equal to 1, so that is the constant coefficient term on the power series representing 1. And then I look at the power series representing x squared, and I can see that the constant term is 0. So I have my P naught and my Q naught. That then allows me to write the Indicial equation. And that looks like this: r times r minus 1 plus r. And that's equal to r squared, and that's equal to 0. And that means r equals 0 is the single exponent on my Frobenius series. And in fact, the fact that it is an integer means that my Frobenius series, in fact, is a regular power series. So let me just note that. And the one Frobenius series is a regular power series. Okay, so I have then now a proposed series solution to my differential equation that looks like this: x to the r, but r is 0, so that becomes x to the 0. I'm doing this so we can clearly see I'm using the same method as before. That, of course, x to the 0 is 1, so that is simply going to go away. So that then looks like this: n equals 0 to infinity Cn x to the n, a regular power series. So then I do what I have done numerous times before. I take the derivative. I get this: n equals 0 to infinity of n Cn x to the n minus 1. I take the second derivative. I get this: n minus 1 x to the n minus 2. I substitute into the differential equation, into that Bessel equation of order 0. So I'm going to substitute the solution and its derivatives into the differential equation, and I will get the following when I do that: the sum from n equals 0 to infinity n minus 1 and this is going to be x squared y double prime, so that is going to be, and I somehow have lost the Cn's on here. Sorry about that. Let me fix that up here. This is when I take the derivative here, that Cn will still be here, and that'll be x to the n minus 2. And then when I substitute in, this Cn will still be here again, Cn x to the n, and it's x to the n because this expression here is x squared y double prime. And then I will add to it x y prime, so this will look like this, n equals 0 to infinity, and here we'd have c n c n x to the n. This expression right here is x y prime. And then I have the final term x squared y, and that's going to look like this. The sum of n equals 0 to infinity cn x to the n plus 2, and that is going to be x squared y. That's equal to 0. So that's me substituting the solution and its derivatives into the differential equation. Then I shift the indices. Shift indices to match powers. Okay, so I'm going to shift my indices so that all of these things have a power of x to the n, and that will allow me to combine them. So the one, of course, that I have to be careful about is that one right there. So I'm going to shift the indices and make all the powers x to the n, and I will get the following. The sum from n equals 0 to infinity of n squared cn x to the n plus the sum from n equals 2 to infinity of cn minus 2 x to the n equals 0. Okay, so these two here combined into this one here, and then this one has been shifted. Okay, then next step, take out the n equals 0 and the n equals 1 term. And when I do that, the n equals 0 term, I get no information. In the n equals 1 term, I find out that C1 is equal to 0, exactly as I did in the previous example. And then I take a look at the n greater than or equal to 2 terms of this expression here, and that allows me to form the recurrence relation Cn is equal to minus Cn minus 2 over n squared. And that implies, of course, that Cn is equal to 0 for all n odd. That's because of this fact here. I'm getting very close. Now I can compute all the even constants, C2, C4, C6, like that. So allow me to do that. I will get here C2 is equal to minus 1 over 2 squared C naught. And then C4, so I'm using this recurrence relationship right there to do that. C4 is equal to minus C2 over 4 squared, and that's equal to C naught over 2 squared times 4 squared. And then keeping going, just another one, C6 minus C4 over 6 squared, and then that's going to be minus C naught over 2 squared times 4 squared times 6 squared. So now I'm going to observe the pattern. Observe pattern. And if I wasn't happy with just observing the pattern and being confident about that, I want to be more rigorous, I would prove by induction. I'm not going to do that step here. And then I would say that c to the 2n is equal to minus 1 to the n c naught divided by 2 to the 2n times n factorial squared. Okay. If I choose c naught equal to 1, then I get this. I get a function, the Bessel function of order 0, which we denote in this manner: j sub 0 of x, the Bessel function of order 0, that is a 0, of order 0, and it is equal to this. The sum of n equals 0 to infinity of minus 1 to the n x to the 2n divided by, I just want to make that really clear, x to the 2n divided by 2 to the 2n times n factorial squared. And I can write out the first few terms of that, see what it sort of looks like. It looks like this: x squared over 4 plus x to the 4 over 64 minus x to the 6 over 2004. And I mean, looking at what's happening here in the denominator, you can see that this will be convergent for any value of x. And so there we have it, the Bessel function of order 0 is one of the most important special functions in mathematics. Okay, that concludes the lecture on solving ordinary differential equations, second order ordinary differential equations that are linear near a singular point. The key to figuring out how to do this was to go through the known way of solving the Euler equation. Thank you.